Thank you for everyone for coming here, and thanks to SchneidersLaden for this for today. So I will try to set up like this conversation in like in two parts. The first one, I will explain you why I'm making this stuff, and like a bit of not story, because we are like a few years old, 4 years I think. And the second part, we are going like more in deep into the module and make some patches and see what they can do. Of course, explaining the reason why we made them this way and what they can do. So I started the company at the end of 2014 because making this Uno foldable case here. For personal needs. Actually, the personal needs will be a recurrent thing probably in all the modules that we are releasing, because they are that I will talk about, because they are kind of, they all have some not unique but very precise feature that you cannot achieve with other stuff. So as anyway, as personally being a mechanical designer, not an electronic guy, not something related to sound, I was a bass player. I have like a sort of classic, let's say, formation. I don't know if it's English. Training, yeah. I came to the synthesizer world for like curiosity, because I was curious in different ways to achieve different sound. And I, like in one of my trips, I don't know, 5-6 years ago in Berlin, I got my first modules, like this one, the Hertz Sonat and the Mats. And I was playing with them for like 2 years or something, 1.5 years or something like that. And I started to design my own case, like probably everyone is doing in the beginning, to save some money too. After a couple of years using my prototype, I came to the conclusion that it was not that strong, and I redesigned it completely. And in the same period, there was like a post, a sort of header on Muff Wiggler that was saying, if some of you have an idea or want to come to the NAMM this year, we are willing to share our booth together with new people. So I said, okay, let's make a prototype and let's bring it there, because maybe someone is interested in getting this thing. It worked out. We went into the production with this cabinet, and after a couple of years, I had the luck. I was attending in Verona a concert of Alessandro Coltini. And I met in there the guy that actually is my PCB designer, and the guy that takes care of the assembly of all the current modules. And he was telling me like, yeah, you know, if you need a power supply or if you need something special, we can design it for you. I have another guy that is very cool in analog design and things like that. So we met, and we started to work together on our first product here, which is like not in the camera, but it's the mixer. Maybe you have, yeah. So we start to work together on this, like we called it like CGM because of the channel group master thing. We designed this modular mixer for in order to this guy in the bottom here. So, in order to have the possibility to set up a mixing solution for Eurorack, which can change over time, basing on the needs, basing on if you're putting it on your small travel case or in your huge system at home, you can just rearrange module, combine them together in different ways. And you know, analyzing what was available in that period, there were not that many mixer with the capability of simple stuff, you know, like mute, sol in place, BFL, or sends and return with VCA, over sends and return. So we said, okay, let's design something together. Let's see how it works. We got a prototype, a first prototype of this guy, of a channel only. It was like something like this size. This guy came from the high-end mods and repairs, so he does a lot of his main job was like repairing and modify and do redesign other stuff for the studio equipment and outboard. And yeah, we had an excellent mixing system, an excellent behavior of the VCA itself. After this thing, since it worked quite well, we started also to have, you know, as soon as we fixed the need of a mixer, we started to do our stuff, to play, and we came up to the point, both like me and Federico, the other guy, that we both needed a random source that was capable of doing several different random voltages, not like one or two. And another point was that if it does multiple voltages, they should not be correlated. They should be random. So when some goes up, the other can go up, or maybe not. Depends. It's random. So we started to analyze what was available, which would have been the feature, because, you know, randomness, it's like a strange subject, because actually it's random. You cannot manage it, but there are a few ways that I will, yeah. Then we will talk in detail about the modules. So we didn't found, we applied a few tricks to better manage 4 different ways of generating control voltages, 2 different ways of generating random clocks, and the SAPEL was the consequence of this test. Together with it, we started to design our utility, like this one in the bottom, the 333. It's like very difficult to pronounce, I admit, but which is our idea of the, let's not say buffer multiple, but of the multiple and like high-end summing system, so like unity gain mixer. So it's a sort of mix between the two. After these two, I had with a few friends in Italy. They were all the time talking me about this 296, like this spectral processor, and like, yeah, it's fantastic. I have to get one. I cannot find a way to get one. And I said, yeah, okay, it's an equalizer. So what is cool with it? I didn't try it yet. I was only looking at some pictures online. Then a friend of mine got one. We played with it like some days, and I started to understand the logic of the way to the Filterbank thing, and the fact of having quick functions to access the bands is lets you manage the spectrum in a different way. So what I did was like making a huge max MSP patch, simulating this 296 in digital domain. We tried out, so you start to analyze the product and you see, okay, there are you can do some spectral transfer, you can do this kind of function, you can do this band scanning. So we started to put, like different bands, how you say them, like crossover frequencies. We started to put several functions that actually are not included because probably they were not useful at all. And in the end, we simulated with Max, Mira, the app for the iPad, and some expert sleeper stuff. We was able to play the module only like on the computer, but patching it with real cables. And that was the consequence in the end. So we announced it last year at Superbooth, and it took also like other 8 months to get it ready for the for everyone. But this is the result. It's 16 bands, completely analog, voltage controlled graphical equalizer with it's the unique graphical equalizer. Yeah, equalizer that has this parametric scanning function. So instead of having only like this, you know, scanning center and scanning width, you also have the possibility to set up the width, center, and the amount of gain that you are applying. So you can, yeah, you can use it also as a VCA. Like in this case. Actually, it's not a VCA. Yeah, there are 16 VCAs in there, but we are controlling all them together. So it's a unusual way to access your signal, your equalization. But for this reason, it can be interesting sometimes. And now we are here today. So
does it have envelope followers?
It has 16 envelope followers. So the module, it's composed of 2 banks of filters. Mm-hmm. They are very similar, not the same. So the main filter bank, it's composed of 16 48 dB per octave bandpass filters. And it's designed to process the audio. So if we take off this control voltage, and we take off a pitch, so this is like, let's say, no, this is not the case, but so this is our original signal, okay? This is our processed signal in the flat, with all bands open. So we wanted to have a sort of very coherent, colorless sounding tool. Because as soon as you have a color that is applied, you cannot obtain anymore your original signal. But as soon as since it is an equalizer, you can do this and obtain a different sound. So yeah, that's what you can do with the first bands, with the first filter bank. With the second filter bank, what you can do is so the second filter bank is composed of other 16 filters, and they doesn't output any audio signal. They just generate 16 envelope followers that are used for they create 16 envelope followers. This signal, this control voltage, we can get it and patch it to another module, of course, but it's semi-normal to the main VCA. So what you can do is, using 2 audio signal, you use one for processing, to be processed, and the other for analysis, and you can transfer the spectral content of like the modulator to the main one. So if, for example, now we apply like we are changing the pitch only of the modulating oscillator, and we see that the spectral content changes, and for this reason changes also the equalization. We can use this equalization together with the graph with the sliders, or we can use any
Modulation to automate the movements.
yes, exactly. So we have several ways that can be combined, several ways to access these filters that can be combined together. Then other stuff in there. It's you have access to the 16 bandpass filter directly. So if you want to, depending on the harmonics that are like a square wave, probably is better. So we can get these signals out, the one we want, sum them together with a 3-3-3, and reapply a VCA, for example, or like using higher frequencies, sum them together. Since you don't have any, you have a reminiscence of the original tone, and you can use this kind of sounds to create a sort of percussion, like not a shaker, but something like that that is not anymore harmonically related to the original tone. And consider that now we are working only with a flat tone, so we are not modifying the pitch, the harmonic content of our original oscillator, So now what we do have is like flat tone, VCA completely open, just a fluctuating voltage that controls the folding level. The wave folder, yeah. And yes, so that is the idea. Another feature that we included in that, this is really a direct consequence of the original 296 design, because that module was using 16 bands only, and what you can do was like having 8 bands transferring their content to the 8 neighbor bands. So actually the spectral transfer in there was a sort of spectral transfer. You're not transferring the real amplitude of that segment of the that audio portion. So you were using the neighbor one. Since we have 32 filters here, what you can do, and we kept the odd and even input, we can use a folded sine, like in this case on 16 bands, but if we apply a second jack, the folded sine wave here goes only to the odd bands, and here we have a square wave that goes to the even bands. Usually what I like to do is like the opposite, because the even bands includes the last one, which is very wide, so from 5.5 kilohertz to more than 20.
And the lower part of the frequency range is as well something like this?
The lower part is usually the bandwidth of each bandpass filters is expressed in semitones, is 5.5 semitones. So in order that each 2 bands you achieve a major 7 interval. In this way, each time you're going from like the first to the third to the fifth to the seventh, you never achieve the same harmonic or a multiple, but you don't emphasize a particular harmonics, because otherwise you can have like, for example, I don't know, B flat maybe always like 3 dB less than the other. So it wouldn't be fair for the B flat.
But the frequencies are of course chosen musically to
the frequency I have to be honest, no.
There's this theory with the critical frequencies.
The Bark scale,
Yeah,
you mean? Yeah.
the Bark
No,
scale.
my approach was like
Totally different.
totally like mathematical or.
Okay.
So even because we like digitally we simulated like several we simulated the booklet 296 structure, the baud vocoder structure, and two ways of our like our filter positioning, let's call it like that.
Yeah.
They all sounded a little bit different because when you do spectral transfer or when you work with sliders, of course they sound different. You have different characteristics. So what we wanted to achieve, this one is a consequence of the fact that we wanted to have like the first band and a little bit the second for the sub bass. So if you have a very dense signal in the lower hand, you can still achieve this kind of punchy frequencies, you know. And in the second one, you can also use it for kick drum, so it stands in that area of frequency. After that, we started with our 5.5, 5.5, 5.5 semitones, and so on.
So they are equidistant somehow.
Yeah, they are equidistant, reaching the 5.5 kilohertz, and then we said go to the maximum because at that point, after 5.5 kilohertz, it's just air. So we wanted to focus on this range of frequency from the third band to the band 15, and this was the result. Of course, as soon as you change them and you move them 20 hertz up or down, it changes the sound. But the fact is that since we can achieve the original sound in this position, we said, okay, probably. If someone has to argue for one configuration, another one will argue for the other. So let's pick one and random, and it's done. Yeah, the other stuff. Since now we are using the two sources, like which are related in terms of phase, because we are getting the square and complex final waveform from the same oscillator. The other thing we can do is that we can use two waves as a modulation. So let's apply a different pattern. Let me find something here. We modify the pitch of this one. Okay. Now it's not interesting, of course, but what I wanted to show you with this is that if we take off the sliders. If we take off the output only of the odd output, so our square wave modulated with this oscillator, let's take off the envelope followers for a second because it's easier to understand what's happening. Now we have a sound. If we use the even output, we have a completely different spectral transfer. It's using 8 bands for analysis and 8 bands for synthesis, and the analysis thing comes from another oscillator. So you can use it as not a stereo but a dual independent processor. Maybe with all the signal coming from one source, maybe with 2 sources. This lets you use it in more flexible configuration. Of course, if we add harmonics, we will achieve better, more interesting results. Right. So another thing we added in the, which is not common in this kind of products, is the ability to apply a slope, integrate the envelope followers in the release time, of course, but also in the attack time. So in the attack time that we have here, now we do have this kind of very knocky change between the different excitement, let's call them that way. In this way, we can have a very smooth transition and we can increase also the release. And if someone wants to have this kind of cloudy modulation for, you know, like drone stuff or things like that, it's kind of something you cannot achieve with other stuff. That was the reason. So to have more ways for processing. It in the beginning it came from the when performing like using a drum sample for as a modulation source, very like hyper compressed drum sample, and we were taking off all the attacks, okay, for this you know, snare, kick, snare, and cymbals and something. So this transition were like smoothed out a little bit, and you can recognize that it was a drum sample, but not that much. I mean, if you were making the patch, yes, but otherwise it will be something like a strange modulators that otherwise you cannot achieve with other stuff. That was the thing. Yeah, so that was this is what we did on the filters. In terms of other quick ways to access this equalization, as I was saying before, like sometimes we have this kind of strange thing, depending on the sounds. But anyway,
so what kind of uses, like for the lay user who is looking at the Filterbank and stumbles upon Fumana, what example, like what kind of use case would you?
The unconventional filter processing, because I mean, if you need a low-pass filter, get a low-pass filter.
Yeah, of course.
If you need I don't know, a state variable filter, go for a state variable filter. Yeah. This is a different way to change the harmonic content. So if you're willing to, like, maybe it may be more related for people that are more into the how can I say, not wave shaping, but yeah, this kind of function. So changing the spectral content of the waveform, and not using it like with a subtractive way, like subtractive synthesis way. So I use it to shape it. It's static, like in there. I apply volt per octave tracking, something like that, and that's my sound.
So it can have a place on every stage of a patch, like as after an oscillator, for example, but as well at the end of a chain.
Yes. Depending on how you're setting up your rack. And on what you want to achieve in that case, because it's not like in a, for example, if you're using like I don't know, a multiband compressor, and you apply at the end of the chain to a set, like as a master section. It can do that, of course. I mean, it can work at the end of a chain, but you have to be careful. You have to understand that. I mean, here you really can change a lot the spectral content of your signal. So yeah, that's what you have to be aware of. But I mean, it's not dangerous. Nothing breaks if you do it like that. But it can be for sure interesting, and gives you. It's complex. It takes time to be understood and to get its potential. And I already seen that there are users that are way better than me playing it. So
like
yeah.
a diff kit video with the docking.
Exactly.
Just like
The patch that I was trying to do like 1 hour ago. So trying. So yeah, it depends on how you're used to patch. And like one of the guy that works, Federico, one of the two guys that works with me, he has a really strange way to use it that I cannot propose you this evening because I'm not able to perform it like in that way.
Well, but it's as well for the good quality.
It's very
of the instrument. Like many of the best instruments that we know in electronic music have always become to be used in ways that were not supposed to.
So
this
I think it's something that happened with the mutable instrument braids that was used like not in the original Olivier idea. So yes. Anyway, let's do something, and in the meanwhile, let's explain also this bottom section because there is. This is another interesting thing. Okay, we do have, we are doing like, let's take off some cables and understand what is going on. So I apply so here we have a random sequence where the pitches are controlled by the semitones output of the sapel. The speed of the thing is modulated by fluctuating voltage of the other section of the sapel. So, of course, we can work like in this way and use it as a sort of high pass, or in the other way and obtain a sort of low pass. If we want to access this kind of function quickly, what we can do is use this and I can synchronize it to I need a sync output, and I have the sync output. Okay. So now we have this kind of, we are using the tilt function only. The tilt function is a single control. That's why it's the only green element in the bottom here. And it works, it does tilting. So assuming there is a sort of fantastic fulcrum in the center here between the lower height and higher height bands, we are doing like this way to the fader. Instead of doing it manually, we are controlling it with a control voltage. And this allows us to have a sort of ducking effect, or depending on how it's set up, this kind of, depending also on the sound that we feed into, this kind of vibrating string thing. The patch that I was trying to do before, which probably I won't be able to do it. I'm trying. I will try. I want to achieve that master level, and so we can combine the tilt and this parametric scanning. So parametric scanning works, like a parametric equalizer. We have gain, we have frequency, and we have slope. So the gain is like the gain, positive or negative, like peak notch. Okay. Frequency is the frequency, and the slope is like our width of our bell. This is not resonating control, because we are not using it as it's not a filter. It's amplitude control for several filters. So here we have peaking or notching way positive or negative. We have center, and we do have bandwidth. So that's why it's we call it like parametric scanning. If So in this case, we are using like several envelopes all linked together. One for the tilt, one for the amplitude of the scanning, and one for the width of the scanning. And
this would be a
the only
sort of
one.
global controls for the module.
Yeah. These are these parameter access. We call them like globals because they are function that access the 16 bands together. For the analysis filter bank, yeah, it accesses the 16 bands, but there are 16 elements. So in this way, even with the fader VCA input, you can access them, but they're independent connection. With this one, with one control, with two cables, you can access them and change your sound. You can also use it as a low-pass filter or as something like that if you want. And yes, that was in the idea. I cannot achieve it properly, probably. Anyway.
There's the classic use of using it as a vocoder as well.
Yes. So the vocoder thing, yeah, we do have a microphone here. The vocoder thing is like, so the vocoder works like, it's very similar, the principle of the way it works. So we have two signals, a carrier and a modulator. The modulator is analyzed, and some control signals are are obtained from this analysis, and are used to manage the amplitude of the carrier. So this can be a vocoder. I mean, we can do that. Let me try to. Let's see if the volume is. Okay. Probably we are very. So my voice goes into this preamplifier. The preamplifier output goes into the modulation input, and let's use sort of maybe a noise. Also. Sa. Yeah, that's what we can do. If we want to apply a sort of pitch control, something that reminds you of a tone, we can merge the noise with a signal, exactly. And unfortunately, I don't have that much amplification here, so I don't know how much it amplifies. Threshold. This section is connected. I don't know this module.
Yeah, it's wait a second.
Threshold.
No, it's
Okay. The pitch is changing. Okay. So. So we see that with my voice, my voice is analyzed, divided into bands, and there is this control voltage created. We see that they are standing usually between in this area. Of course, basing on using like different voices, using different microphone, using like preamplifier thing with several different characteristics, you can obtain a better vocoding, even with a better voice probably. But the principle, that is the principle. We also do have a voice section. Let me try it out if it works in here. So let's use the pink noise here and the white noise. sa, sa. Okay, the unvoiced is a strange thing. The unvoiced in the vocoder is a control that is used to recreate a certain part of the human speech, and like this s, th,
Sibilants and fricatives,
yeah,
and
that kind of sounds. So, basing on your way of talking, actually, this kind of frequencies are usually in the yeah. To better explain what it does, if you have an idea of the deesser thing, that thing is like the opposite of a deesser. So what it does is instead of analyze that part of the spectrum, so usually you have a very strong sa thing. Yeah, there was I had the volume sa down, sa sa sa. So there is a little bit of noise coming out now. The unvoiced section works on these two bands. These two bands are analyzed when there is like an S sound or a fast transient. It creates another envelope, like the 17th and 18th envelope, that goes to control other two VCAs that are applied to this input, to this noise input that you can patch to any kind of noise, like white or blue or pink. Usually white and pink are better. These signals in the Fumana are summed to the original signal in these two bands. So they came out from the main output, of course, and they helps to recreate the original, to better recreate, to better vocode. We say it's different from the normal vocoding because normally the vocoder has a sort of not dry wet, but they blend directly. The main signal is not used anymore. It used only for a short amount of time the noise with a certain percentage, and so it's not like added sum together. It's like this or that one.
Crossfaded somehow.
Yeah, it's crossfaded. Exactly. That was the word. We decided to use it in this way because if we are not using it as a vocoder, that probably most of the people are not using it as a vocoder, what we can do with this control is feed it with an oscillator. So, I mean, it doesn't break. So, if we feed it with something like that, and we do have a modulation signal that is not coming from here, but is coming from, let's say, as soon as we start to go up to this band, we hear that there is something else summed together. With the original, okay, summed together with the original signal. Of course, this depends on your modulators. This one, yes. There is something. There is. Modulation is closed. Modulation is closed, like this. Okay, we're using one here. So now This is this second oscillator is the one that is summed in this band. This terrible noise here that we hear. We can use it as another input for anything you have in mind. It's there. If we would have switched, use it in the switch version, so switching crossfading between the two sound, you're not capable of summing the signals. So you cannot use them both. That was the reason actually. So yeah. Other last few things that we added here are, we said that we do have different output, one for the odd and one for the even. So if we use them both, technically we can hear modulation. Okay, technically we can use the odd output and the even output and sum them, but we need two channels, or we can use the all output. The difference between the two, we made different equalization between the two. So actually the original, the pure output is the odd and even, combining them together. The all output has an additional low pass filter, like at 18 kilohertz, something like that, like 3 dB per octave, very soft, yeah, just to improve a little bit the global feeling, make it more soft, you know, more pleasant for your ears. But in case someone needs like very knocky sounds, you can use these two, and you will achieve the real. This oscillator cannot go up to there. Really harsh. While this one is a little bit softer. So the other difference is that if we're using these two and we combine them together, so I'm summing them in this
the unity mixer.
The unity mixer, and putting them, or maybe we can use this. Yeah, let's use the 3-2-1 because we have attenuators. So, sorry, I changed my patch. Let's take off this because I don't need it. Let's take off this because I don't need it. And this is our output. I'm using like the odd signal goes to the first channel. The even signal goes to the second channel. We have our original source. We can swap the phase from the module of the two outputs. So when we are summing the, like, we have like two comms, you know. So the waveform, the spectrum coming out from this output is not flat. It's like 8 peaks with a low shelf on one and a sort of high shelf on the other. When we sum them together, we can swap the phase of them. So if we swap the phase, what we can do, or what we can achieve, is like use one signal to decrease its content from the other. So you have even more possibility, excluding the fact that we have this kind of maybe equalization. That was not one of neither like mine idea or an idea of the other modular guy that works with me. It was an idea of like the analog designer, because it said, in this way, even if you're using like the second, for example, you're using the main output and you're using the even output processed with a like delay, and you're processing it in phase opposition, you will obtain like very different sound, very different presence on the delay, on the reverb, or on the tails and things like that. So it changes if you look at with like it's called goniometer to see the phase relationship with them, they're kind of very, very, very interesting. And that's it. So yeah, if someone has any question or nothing related to Fumana, no, okay.
Question: can you feed it with noise just to like show? Because I saw Alexandro Catini do it with his Buchler Filterbank, like do hi-hats that can have different sounds, like just his.
Yeah, you can do.
Things, different bands to then get a bit more percussive on certain bits of the spectral range.
I'm not Alessandro Platini, so don't expect me to. Otherwise, I won't be here probably. Kidding. So yeah, you can ping it. You can use clock to ping it. Using clocks. I mean, I don't like the distinction between the clocks and the envelopes, because actually they are all, it depends on their length, you know. So using clocks from different kind of envelopes, that actually I requested to have 2 envelopes like equal. That was my fault. But if you have like two different envelopes, 2 different clock generator, probably they will have different clock length, like I don't know, 2 milliseconds and 1.5. Even the you know, each time you ping a band, you are creating other harmonics, because your sound probably is open and closed, not at the 0 crossing point, but so using several envelopes will result in different way of each band behaves. And if we are using the clock from the Sapel, yes, probably it's too much fast. Okay, we can have it like I took off something. This goes to the input. So I didn't see the patch, but actually, yeah, you can use different noises. You can use a pink noise or any, like the red noise that we have in the Sapel is very, but due to the, since it's so fat in terms of, you know, lower hand harmonics, actually you have the, it seems that it's very lower in volume than the others, but actually it's just because there are, you know, so much low end content. Then if you use output from here, okay, so we can take off this thing and take off this thing. So yes.
I mean, even this patch shows very well that it can, I mean, it generates a sort of cloudy-ish kind of sounds, and at the same time just feeding simple noises as you propose it. Yeah, it can be really, really versatile.
Another thing, if you do have if you put an envelope into the...
You need one more?
I need another envelope. No, I take off something. No, it's not a problem. It's not a problem.
We have one here.
It's fine. It's fine. If we apply an envelope to our modulation, I mean, the modulation bank works for the audio, but actually it's just terms of frequency, you know. So you can obtain this. I need more volume. Okay. You can obtain other like excitement, and you can reuse these bands to ping other stuff, to ping other bands. So the only rule that it's the only rule that it has is that you can take off any of the 16 signal and trigger anything. Like you can trigger a drum loop from that. As soon as you patch the input, the envelope follower is bypassed, so it's semi-normal. So you take off the envelope follower thing. So if you need to sum the envelope follower and another VCA signal, you have to take off the envelope follower, sum it in another point, and send it back again. So that's the only limit that you have in there.
Any other questions? I think that's way, lower the volume of the speaker.
Yeah, my fault.
Yeah.
So maybe I can explain you the random source in case someone is
It was
interested.
already being used.
It's like
but you can.
I
you
used
can
it.
run
Maybe I will, instead of explaining you how it works, how it what it does, I explain you why it's designed like in this way and what is the difference with the other random sources. So yeah, the difference is mainly there are two differences. The two differences are the way the noise is generated, the random signals used in there are generated, and the way of the quantized voltages are generated. Usually, as far as I know, in this, like if you think about the source of uncertainty, what you do have is like a sort of digital noise summed together with a triangle oscillator in order to cover the whole spectrum, you know, correct amplitude, you know, and this noise goes to this. There is this kind of shift register thing that takes care of your quantized voltages. I won't go into technical detail because it's not my stuff. The request that I had in the beginning is that, I mean, just a point. Using that approach, the result of your quantized, let's just take off the patch because it's better to listen to it, and it's easier to understand. I mean, if we do have I will take the pure sine oscillator. So, volt per octave, 2 to the n. Semitones. Sine wave, semitones modifying the pitch of our sine wave. What you do have usually is that you set the number of bits for this quantized voltages. Okay, so we goes from 1 bit, so 2, up to 6 bits, so 64, I think, yeah. And we are passing in this way from like 2 to 4 to 8 to 16 to 32 to 64. We don't pass through 63, we don't pass through 36, so you only obtain these groups, And the other difference is that as soon as you add bits, you have a sort of, if you think about the magnitude of this signal, the amplitude, you are adding a resolution to the grid. So in the beginning, when you have like 2 voltages, you have like a couple of volts of distance. Then you are you adding other 2 points, which are like one in the middle and one upper, and so on. So from the beginning, you have this very distant behavior from your original voltage. I wanted to achieve the opposite, because when you are moving, if you use it to, not to change a pitch, but to change the way it does wave folding, for example, we would have achieved something like this from the beginning, like very open and very closed. In this way, we can have something that gradually, this random voltage goes far away from the original value, and yes, it's more manageable. That's what we wanted to achieve. As soon as I increase the volume, now we are close to the 64. And there are no 32 or 64. It's like in the middle. So sometimes it's 32, sometimes it's 40. It depends. It's random. You can control and you have separate control for the semitones and octaves output. So you can do. Can modify with an external CV or as you want. The other thing was like related to the signal itself used for this random generation. We wanted to stick with a complete analog design, and after a few prototypes, we found a way to use thermal generated noise. So like really. It's random, okay, without having the problem of the, like radio frequencies pick up or things like that. So everything in the module, it's like shielded. You can put your phone on the back of the module and nothing will happen. It won't affect the noise signal actually. Okay. So these were the 2 things. The second way, the last thing that is one of the usual questions that I have is referred to why it's double and why it's so. Because if I have made one channel only the yellow channel, it will then be like smaller and cheaper and so on. The reason is simply that with one of these you have enough randomness for a system. That's all. That is simply and even because you can have a green section modulate the speed of the yellow section. You can cross modulate them. So let's use for example this. In this case, we have the fluctuating voltage, or we can have also the.
By the fact of being 100% analog, there will be never a repetition, right? Because with
no, there is no. It's
on the 266 source of uncertainty. I think there was a digital part.
I think so. I'm not that expert.
I think that there was a level of repetition.
Yeah.
Which would be like, I don't know, maybe 3 days. Every third day it would repeat or something. But
probably yes. For sure. No, here no. It's thermal noise, and the transistor used for this generation are like hand assembled on each module after the manufacturing assembly. So they are selected, and all of them have their own matched resistor to have the proper noise amplitude. So it's kind of a precise thing. So yeah, these are the thing that you won't probably find on the website or on the manual, but these are the reason of this design. So I think it's all.
Yeah.
If
Anyone has any questions about any random questions? I have to use the pen. Come on.
No. Shy. Okay.
Shy.
No. In case it's. I think it's here at
We
your
have
place
it here,
all the week.
yeah. We have
all
it
the weeks.
here. You can come over every day from Monday to Friday, from 2 to 6, and try it out by yourselves. And
Yeah. And sooner or later we will start making also our videos to explain the module, because we were quite busy in the I promised videos, and I didn't make them yet. So they will be online. I don't know when, but sooner or later they will be up.
Superbooth will provide as well some video material probably that you can use.
Yeah.
So
Yeah.
Are you thinking more of making proper demo videos yourself?
Probably I will make them like in the summer. I will make some deep explanation, even because even explaining the vocoder thing and so on, you have to use proper sound, and take time to to explain it. Even the band things. I mean. The fact that I want to make a video only to show, like, for example, okay, that's a square wave, and this is what happens with the 16 slider open in this way, and we are matching something close to the original square wave.
Yeah.
Of course, it can be perfect because it's processed, but that's what it's gonna happen. Even because, last thing, we are very proud of that, and I'm very proud of my analog designer. We achieved less than 1.5 dB of tolerance in the transfer function of all the filters. So it's extremely precise, and that was one of target reach, So.
Very good. I mean, this is just from the faceplate, it oozes quality. And the sound, of course, it is corresponding to the build quality. Yeah.
Okay, so
thank you very much.
Thank you for coming.